So we're just going to give a little overview of the kind of introductory sequence that you would take in computer science and AI, and then talk a little bit about some lessons that we use in our CS100 course. So these are the introductory CS courses here. Again, these are all used for computer science and AI. Now, for the AI degree, the CS 350 and 351, the last two listed there are actually electives. They're not required courses. But in general, most students are going to start with this kind of sequence. And this is over the first 2-3 semesters at IIT. So CS100, that's the introduction to profession. That's a standard thing on IIT's campus. All new students take an introduction to profession in their major. If you want to go look at that webpage later, you can see what we did last fall. So it's just mos.cs.iit.edu. And really the point of CS100 is to show kind of the breadth of computing. Now, many students come in with some sort of maybe programming background from their high school. And we just want to show that there's a lot more to computing other than just programming. And that shows kind of a breadth of CS. We also have some, ethics and computers and society topics and some project teamwork type assignments too. Our CS 115, 116 is a 2-semester object-oriented programming sequence. It matches the AP CSA. We happen to teach Java. So again, if you have no programming background, that's fine. You'll start with our CS 115 in fall. If you come in with some background, we also have a 1-semester accelerated version, CS 201, which covers both 115 and 116 in one term. So it's truly not, we don't teach it like a syntax course. Programming can be a lot more than just syntax. We're trying to do problem solving. We're doing, design, object-oriented design. We're doing testing, things like that. So it's not just a language course. It's a true introductory to like software engineering, object-oriented programming. Then CS 330 is discrete structures. That's actually kind of a math class. It's the math behind computing. So it's logic and proofs, some stuff about algorithms, but we're not implementing. We're talking in the general case algorithms, recursive algorithms, some counting, probability statistics, combinations, permutations, some formal grammar, language, and then some kind of the data structures, but from the theory point of view, trees and graphs and things like that. Then Michael's going to talk a little bit about the last 3 courses.
Hey everyone, this is Michael. As Matt said, both of us teach quite a few of the undergraduate courses you'll be taking at IIT. And among the courses that we actually take turns teaching is CS 331, Data Structures and Algorithms. Data structures, some of you I imagine may have heard of. I'm sure all of you have heard the term algorithms before. Data structures and algorithms are key to, well, just about all high-level computer science. We cover the data structures, the essential structures that allow you to store and manage and access data, search through data. A lot of data structures that we cover in this class. We also cover early on in the class the Python programming language for those students that don't yet know it. Some of the lower level classes are ones where we take the opportunity to expose students to a number of different programming languages. As you move through the curriculum, we become less and less language focused. Indeed, the higher level courses, you're free to use whatever language you use, obviously sort of within the requirements of the class. But early on in the curriculum at IIT is where we sort of show you a bunch of different languages. I also teach another class that's not listed, that's 340, where I cover functional programming, where I talk about the Haskell programming language, which is a super cool one. I love that class. I'm teaching it right now. CS 350 and 351, listed the last 2 on this slide, are part of the systems sequence in the CS curriculum. And 350 starts by covering computer organization. So it sort of covers the hardware side of things. You have to understand some of the hardware side of things, assembly language, how you encode higher level data like integers and characters into binary. You have to understand that stuff to be a good programmer. So that's something that's addressed in that class. And then after having taken that class, you move on to systems programming, which I'm teaching this semester as well, in fact, where you learn about what the operating system gives you, the programmer, in terms of abstractions. So you can sort of see a theme that you kind of build from the bottom up in the system sequence, where you learn about the hardware, and then you look at the next layer of the onion, and then you just keep moving up. After that comes operating systems and so forth. I think these classes give you a good sense of how the core curriculum in the computer science department, and of course for other related majors, give you the background to understand what you're doing when you get to higher level courses. Next up, we're going to talk about careers in AI at CIS and CS.
So, I mean, the breadth of careers with a computing degree is just unbelievable. I mean, we just kind of listed, many of our students' first job is some sort of software engineering related. Now that's expanding a lot we have both our AI degree and a specialization in data science. Data science is a very popular field now also. So we are more, on the analytics side, using machine learning, things like that. We also have a good specialization in security. So some of our students are working in the security area. Now these three that's not limiting you. I'm just saying these are the three largest fields for usually someone's first job when they graduate with a bachelor's degree from IIT. Our companies are, more like consulting companies or, back office for like finance or insurance. That's big in Chicago, small startups. Chicago is great for a lot of entrepreneurial type activity. Our students of course, go work for Google and Microsoft and things like, Silicon Valley or around Chicago. Currently about maybe 20% of our students get a graduate degree. Also, we have a co-terminal program, get both a bachelor's and master's in 5 years. And so it's a pretty good percentage. 20% of our students do get a graduate degree because they want to continue their studies while, right away. And there's also a financial benefit. Your undergrad scholarship gets extended for another year. I don't know, Michael, you want to add anything about careers?
So just this past weekend, one of my former students checked in. Matt, you probably remember him, Vanish. He actually left and he started working at Google, and he's been contacting me every couple of months. He checks in with me. It's great to hear from former students, and it's been fun to watch the trajectory of his career, which mimics that of a lot of other students. They leave, they sort of go into a traditional software engineering job. He started at Google, and then he actually resigned his position. He's like, I'm done here. This is just not like, it doesn't allow me to sort of grow in the way that I want to. And now he's working at a smaller biotech firm out in Washington State. Him and another friend of his actually are rooming together. They're both former students of mine. This is a good list, sort of, that sort of catches a lot of students who are like, all right, I get to figure out what I want to do. And at IIT, we believe that, there are all these fundamental things you need to know how to do, and it prepares you for a career. But obviously, when you get into your career, that's when you start figuring out what you're really interested in. So I think that's a good segue in the CS 100, right, where we start to talk about the breadth of CS.
I want to say one more thing. I always, it's changed a lot from when Michael and I were students. You're going to have not just multiple jobs, you're going to have multiple careers in your career. Okay, I mean, like my generation, my parents' generation, you choose an area, that's your career. Well, now you're going to really have multiple careers. And in general, our program is strong software engineering, and software engineering is going to be needed whatever career you move into. So there's a question of, are there open to research assistants? So let's answer that real quick. Yeah, our undergrads are able to do research with our faculty. Our faculty are interested in finding talented undergrads because you stay here longer than our standard master's student. They're gone in 3 or 4 semesters. So there are research opportunities, including paid summer internships with faculty, or sometimes for credit, doing research with faculty. So any other questions right now before we move on to our CS 100? Chicago Mercantile.
The answer to that is definitely yes.
Yeah.
I know some people that are at the CME.
Yeah, finance is big in Chicago. So also, especially if you want to do the data scientist, we have some of our faculty who teach like the data mining course, specifically work in, Michael, Jawaharlal Panchal, he works in finance. Yeah. So, I mean, the application's taught in that. A freshman to minor in okay, so officially at IIT, the minor is in a not the same subject as your major. Okay, so like if you want a minor in economics, yeah, that's great. But if you're interested, like your CS major and interested in AI, you can do a specialization in AI. It's just a different term where you're going to do a lot of depth work in that area. So you minor in another field, but you can do a specialization in a related field. Okay, so, okay, so, I mean, for security analysts, there's, at least at IT, there's kind of two opportunities. We have a sequence of courses, undergrad and grad courses in security, information security. It's very broad. It's, network security, application security, data security, policies, procedures, things like that. And it's kind of more on the theory side. Separately, we have an information technology department where the more hands-on technical security hacking type tools are used. So you could also get a minor in that. So there's a lot of opportunities for security. Obviously it's a popular field right now. We're officially NSA certified, so it opens kind of government security analyst type jobs to our grads. Okay, so why don't we move on? Why don't we move on to CS100 a little bit? Okay, so one of the kind of goals of CS100 is to talk about computers in society, ethics, and also to get the students to kind of form this community. It's not just in a lot of the work. Oh, actually, I think Michael, all the work in CS100 is teamwork, right? I think it all is teamwork.
Yeah, for sure. Yep.
Yeah. So one of the things we do is we have these debates throughout the semester. Now, last fall we ran it a little differently because of COVID and everything. This fall it's going to be small in your small lab section. You do the debates. But here's some topics that we talked about. You can kind of see the breadth of topics and kind of current areas where you're going to be assigned either a pro or a con side of a debate. It's a team of 3 to 4 to 5 students, something like that. And you're going to prepare ahead of time. You have a week to prepare. And there's a very scripted out how many minutes for pro and con and rebuttal and all that. The rest of the students are going to do a little survey before what their opinion was and if you swayed them with your argument. And it's a standard kind of debate on these topics. And there's always great new topics related to, computation and society and ethics and things like that. So that's one of the assignments. You probably debate at least twice in the fall semester. You'll be assigned random team members in your lab. You'll be assigned randomly a pro or con, and you'll be able to debate these topics. So, Michael, you want to add anything to that?
I think that, just to reinforce what you said, I think that it's critical to emphasize the fact that computer scientists live in a very, very connected world, and oftentimes we're the connectors. But I think there's an important aspect of sort of culture to address. I think a lot of computer scientists tend to be very haughty about our abilities. We're like, oh, we're the guys that build things. So just tell us what to build and we'll build it. Without often, sort of thinking about whether we should, sort of what sort of moral ethical obligations we have. When building these things. A very interesting example is algorithmic bias, in, for instance, facial recognition technologies. I think that's listed over here. That's something, it's a huge societal issue that we play a large part in, but I think a lot of times we seem to just, we take on the technical burden, but we feel like we take on zero ethical and moral burden. And that's something that we want to emphasize in this class. We go out, we certainly, want to continue building more interesting technologies, but we also want to be very cognizant of the way that our technologies touch and impact the world.
And the other thing, at least I see when the students are doing this debate, it really brings out the diversity of the students, the backgrounds of the students, cultural. It just, you really start to listen, like, well, maybe my life hasn't really been exposed to all the diversity of these issues, and I'm really hearing other opinions on them. Okay, so why don't we move on, Michael? Let's move to the next. So I'm going to spend a couple minutes now talking about one lesson that I do in CS100. Again, this is a breadth of computing, and this is actually toward the end of the semester. Actually, we can make these slides available, right, Michael? We can.
For sure.
We'll put it up somewhere and send a link. So I talk about game theory, and so game theory in the sense of playing, 2-player games, computer playing chess, checkers, things like that. Okay, and so I do give a background. Again, this is a topic in game theory would be covered in maybe our 480, our AI course, or maybe one of the graduate ones. And so I'm only going to spend one lecture on it, but basically the idea is this is for two-player games where there's some sort of alternating moves. There's some sort of set of legal moves. It's a finite. There's some sort of define what's a win, what's a loss, what's a draw. And there's some way to kind of the game board, the board of the game is viewable to everybody. Okay, so it's not like playing cards where you don't know what cards everyone else has or what cards are still in the deck. Everything's visible to everybody. There's nothing hidden. So these are standard two-player games. Okay, so game theory is an approach to have a computer play one of the players for these two-player games. So you've all seen stories about this. I think the latest ones, they're getting good at the game Go, which is much more complex than just chess or checkers. Chess took a while to get a good computer playing chess. So I give a little introduction to the theory. So the whole idea is it's kind of like how when you're playing tic-tac-toe, right? You're kind of looking ahead a little bit, right? You're saying, oh, if I go here, what are they going to do? And tic-tac-toe is pretty small. You can, checkers is a little more challenging. But again, you're kind of looking ahead, right? You're saying, oh, if I do this, what do they do it and what can I do? It's that type of idea, but the computer, of course, is really good at looking ahead and kind of trying a whole bunch of possibilities, not just for their own moves or for the opponent's moves. And so the idea of game theory, it's the computer's managing these all possible plays, looking ahead a certain number of moves, because there's a time limit usually. And sometimes you look ahead those certain number of moves, it's an end game. I know who won, okay? And so that if it's an end game where you won, you want to go that way. If it's an end game where your opponent won, you don't want to go that way. But other look aheads are to a game board that is not a final game, right? That's not an end game. It's still in progress. You can't always look ahead to end games. The possible moves are just, it's too large. So the real interesting part of game theory is you're looking at a board, like a checkerboard, for example, and trying to figure out, is this good for me or not? Okay, without knowing this is not an end game, is this good for me or not? So there's these non-terminal configurations that you're going to have to somehow use a heuristic, use some human knowledge of the game. And then the terminal configurations are easy. If that's a win, hey, I'm going to rate that really high for me. If it's a loss, I'm going to rate it really low. If it's a draw, somewhere in the middle. So let's go to the next slide there, Michael. So this is showing an example for, okay, NIM is a little game. You alternate taking away usually little sticks, and you can either take 1, 2, or 3 sticks. If you take the last stick, I think you lose. Yeah, you take the last stick, you lose. So this is for NIM. We're starting with four sticks. I can either take 1, 2, or 3 away. And if I take 1 away, it leaves my opponent the 3. So you can see there's alternating moves. There's the bold level and there's the underscore level. So it's alternating moves. And this is basically doing the entire game tree for NIM. Now, if you see, if it was my level and I chose the last toothpick, I lose. Okay, so if you're on that 1 underscore, there's only one option. You got to take the last toothpick, you lose. So if there's a 0 on your level, you won. A 0 on the bold level is a bold person winning, the one who went first. A 0 on the underscore level is the underscore person winning. So this is showing the whole game tree. This is everything that's possible. So if you look at this and you were going to go first and it was 4, what move would you make? Okay, so just kind of look at that and what would you do? You could type in the chat or turn your mic on. If you go first and you could choose 1, 2, or 3 toothpicks, what do you choose? So and you want to win. Yeah, of course you're going to choose 3, right? If you choose 3, there's no option for the underscore person other than to lose. If you choose 2, there is still a way to win, but it depends on the opponent making a mistake, right? If you choose 1, again, there are ways for you to win, but you're giving the opponent an opportunity. They've got to make a mistake for you to win. Okay, so this is one that we're seeing the entire game tree. We can plot it all out. And obviously the only way that's assuring me to win is to choose 3. Okay, so let's look at the next slide a second. Now this one I changed a little bit. I took off the how many I chose, okay? And instead, those numbers, the +1s and the -1s, are actually numbers passed up from the bottom, okay? So if you look at the lower left, that's a 0 for the bold. That means that's, and it was bold's turn up at the top. That means that's a +1. I mean, that's good, okay? So I pass a +1 up. Now on the next level, or the underscore level, there's ones that are the underscore 1. So those are -1s. Okay, so it's just doing a simple rating of if the bold wins, it's a +1. If the underscore wins, it's a -1. And we're passing those scores up. So when it's my turn, I look at my children and I am trying to maximize the score because a +1 is good. If it's the underscore's turn, the underscore person's trying to minimize the children, pick the minimum of the children because -1, it wins for the underscore. So it's this sequence of alternating. I'm trying to maximize, but they're trying to minimize. I'm trying to maximize, but they're trying to minimize. And we pass all the way up. You can see that it ends up that it shows you the +1 way to go is choose the 3 toothpicks. Okay, so I'm just trying to get a little more of the theory that's behind it. It's this min-max algorithm, basically. I'm trying to maximize, the opponent's trying to minimize. Now, if we change this a little bit and say, well, this is not NIM, let's think about checkers. Okay, well, checkers, this tree would be huge, right? And to get to the terminal ones it's a long way down. So instead, you're going to have to, let's say, because of timing, you can look ahead 5 moves per person, so 10 moves total. You have a bunch of non-terminal checkerboards, and you want to try to rate those checkerboards good for me, a big positive number, or bad for me, a big negative number, or somewhere in the middle if it's, a kind of unknown. So the assignment that the students actually do is come up with some different ways to score the board for a non-terminal configuration from my point of view. If you're, red or black, whatever, how do I score the board? And so these are the little questions we give them. So I want you to help me kind of answer these questions. So in checkers, do you think every piece should be given the same value towards winning? So you're looking at a board. There's a certain number of reds, a certain number of blacks. Should we rate everyone equally? Should I just count checkers, or should we consider something else when we're rating the board, we're scoring the board? Okay, so yeah, different, that's a good idea. So how different? Like, what do you think? And then the second question, are all locations on the board the same value? Or are certain locations worth more if you were going to score that board? Yeah, so certainly you could do things like kings. Kings are worth more than because they can move in both directions. Now, should it be 2 to 1? Or is a king worth 3 times as much? You got to figure that out. How much more powerful is a king? So that certainly every piece is not the same value, maybe. What about locations on the board? What do you think about that? So yeah, some locations are more defensive. Like if along the edge, you can't be jumped, right? So along the edge is good. It's kind of a good defensive position. You can't be jumped. Or a position where one of your own checkers is behind you. You can't be jumped. Or as you move across the board farther, maybe those positions are worth more because you're becoming closer to a king. But are they worth as much as a king? Maybe, you got to figure out that kind of, that scoring. How about, do you change the strategy as the game progresses? Okay, what do you think? When you're playing checkers, does it matter? And again, this really has nothing to do with computing. It's just, I'm showing you that the heuristic in game theory needs the human insight. Okay, so as the game progresses, do you play differently? Or, maybe if you're down a few checkers, should your score the board change depending on how many checkers are left? So what do you think? Or also the next question, who goes first? Does who goes first make a difference? Should you have a different strategy if you're not going first? Yeah, so yeah, you could somehow strategize based on what you see them doing. Now again, this is the basic game theory. The really advanced, checkers things are using game theory, chess things are using game theory, but they're also using a database of all the possible plays of professional masters of the game, and they're looking things up too. They know all these strategies, but they still are using game theory too. So the last idea is kind of a complex idea. So if you think, we have these computers playing each other in our CS100. They write your little heuristic, you play each other. There's no point to play another computer more than once. Whoever wins the first time is going to win every time, unless you put some sort of randomness in, okay? Where as you're scoring the board, maybe you had a little randomness once in a while, so it's not always going to play the same way. If it's built in, this game theory, and you're just scoring the board, it's always going to play the same way against the same opponent. So we talked to the students about, well, maybe you should add a little randomness in your score, so every single time it doesn't always play the same. So you can see there's a lot of concepts in here, and this is toward the end of the semester where you've already done some programming. You can understand how to write the code actually to score the board. It's a doubly subscripted array. And it's kind of a neat little competition we do at the end of the semester. I write all the code for the game theory. You just write the score the board. Okay, so any questions on that right now? We could, Michael could move on to another topic. The students need to take, the ALEX exam is a math placement. So everyone's going to take the ALEX exam unless you have calc credit coming in. You have to pick at least one major. You can't just have two minors. You could have a major and a minor, but you have to have at least one major. Go ahead, Michael, why don't you take over a little bit?
Okay. So I'm also going to talk about a sample lecture. I'm going to go through very quickly some sample material I go in class, but very quickly, I want to first talk about the team project. So the team project in CS100 is on top of, and Matt already said that everything else is also a team assignment, but the team project spans the entire semester. Anyone here heard of the Kurzgesagt videos on YouTube? Pretty popular channel, I think. Anyone hear of them? Yeah, they're great, aren't they? They do a great job sort of distilling fairly complicated and often sometimes even controversial material, right, down into sort of the facts. They're very well researched. The team project in CS100 is essentially a Kurzgesagt style video. So it's done over multiple parts. We ask you to submit a pitch at the beginning of the semester, kind of like an elevator pitch, but this is for a video instead of a product you're trying to build. We ask you to storyboard it. We ask you to come up with a draft video and then produce a final video that we watch and grade. Of course, the last time we ran this, we had to do it over Zoom and we had to watch them after they were sent in. It's a lot more fun when we can actually be in class and maybe sample some of the best together. The basic idea is, again, in CS100, we're really trying to emphasize the fact that CS has a lot of potential social impact. And so we ask you to present some sort of CS topic along with its social impact. We ask, of course, that you research the topic thoroughly and that we can examine the script. So I think the question is sort of semi-related to what I'm talking about. The question is there any exposure to business programming like HR, marketing, production, logistics, trading? So I would say that if you're talking about such business specific stuff, a lot of that material would come from taking classes, either maybe you're minoring in finance or management or something like that, or you're taking other classes where that domain specific stuff comes into play. There is another program where you are forced to work with people in other majors. There's our iPro program. We haven't talked about that. Maybe that's something else we can address during the QA section that will allow you to sort of work with people in other fields. Will we learn anything about autonomous systems? Certainly. So autonomous systems are addressed in arguably a number of different classes. Autonomy is sort of a blurry term. So we could be talking about very low level, simple autonomous systems that are embedded systems that are driven by finite state automata. We could be talking about systems that are driven by machine learning algorithms. Those you can explore by taking machine learning or AI. There are various types of autonomous systems. Absolutely, that's certainly something that can come up in a curriculum. All right, keep the questions coming, and I may ignore some of the questions if they're not pertinent to the current slide, but we'll certainly address them when we get to the QA. Okay, just to finish up this slide on the team project, past videos have included discussions of the ethics of self-driving cars, which is a lot of fun. If you haven't explored that topic, you can Google that. You can see that there are some interesting sort of thought experiments when it comes to how self-driving cars should make decisions. Algorithmic bias, I already talked about that. Encryption backdoors. You can see there are sort of a lot of areas in which the decisions we make as developers can have a lot of social impact, right? And the team project is meant to address that facet of computer science. I'm going to move on now to a snapshot of another lecture from CS 100. I think I have a little bit of time to do this. I want to make sure that I have plenty of time for the QA at the end, so I'll go through this a little quickly. I'll answer that, Alex, later on, right, when we get to the QA, because I have already addressed that. So one of the lectures that I give in CS 100 has to do with complexity. Complexity is a huge topic. The word itself, right, complexity, basically means that we've just got a bunch of different things that we're thinking about or considering, right? And probably, since this is a CS class, we're talking about some sort of software system, okay? The way that we deal with complexity in computer science is pretty much the same way that it's dealt with in other fields, and that is by building systems at an abstract level, being able to build black boxes that we can reuse. And so the notions of reusability and composability are incredibly important. I think reusability is fairly self-explanatory, right? Reusability means that you build something and you can reuse it. So for instance, if you come up with a sort algorithm that can sort a bunch of numbers, you also want to be able to sort a bunch of words, sort a bunch of strings, sort a bunch of objects, sort a bunch of students with different IDs or grades, that type of thing. So reusing an algorithm, reusing a piece of software is a pretty simple idea. Composability is another idea, however, that's perhaps a little less obvious. Anyone heard the term composability before? Any guesses as to what it means when we say that a system or a module or something in general is composable? Anyone? Give you a clue. It has to do with function composition. Sorry, go ahead.
You could use it for a lot of different backgrounds and situations.
Okay, okay. You can use it in different situations. How is it different from reusability, do you think? Okay, so Chelsea says to build from the ground up, maybe? Not quite. You remember what it means to
Maybe
take two functions and compose them? Go ahead, Benjamin. Sorry.
Maybe how easy they are to make them.
How easy they are to make them? That's not, okay, so John says dealing with the relationships between components. That's a pretty good guess. Composability does have to do with components. And when you think of components, you think of, all right, so when I build a program, you have a lot of little pieces, right? And you take the little pieces and you glue them together and you come up with something bigger. Does that make sense? So I think an easier example is, let's say we're building a car, right? So let's say whatever, Tesla, Nissan, or Mercedes are trying to build their next car. They're not gonna, very good, Wyatt, yes. How easily can be combined with other modules? Yes. So car manufacturer is not gonna be, coming up with an entire drivetrain or an entire engine each time, right? They build a new car. They're gonna be reaching onto their shelf and pulling off components that have been built. Since the components individually work, they can put them together and then they build this big thing that also works. Composability is critical. It means that we can engineer a module, some library or some small piece of software that we can test thoroughly, make sure that it works, and then we can put it away. And the next time we want to build another piece of software, we can pull that out, combine it with other pieces of software, and construct a gigantic, more complicated, but still very predictable piece of software. Composability means, exactly as you say, Wyatt, how easily can it be combined with other pieces in order to make a bigger, piece? Composability is critical. Without it, it's really hard to build large pieces of software. Unfortunately, there are some things that defeat composability. I won't throw this question out there because we don't have that much time to sort of ponder possible answers to it. But the two big things that defeat composability are state and concurrency. State is something that most of you who have done any sort of programming recognize as sort of just intrinsic to programming. Like when you assign a value to a variable, that value has a certain state. If you change the variable, for instance, if you increment it, it has a new state, okay? Question from Wyatt, isn't something that is reusable generally also composable? That's an excellent question. They're actually subtly different. So something that's reusable isn't necessarily composable for a variety of reasons. So one reason in software where something is reusable is not composable is because it might not be designed with a good API. It might not be designed in such a way that it's able to easily sort of Lego together with another piece of software, right? So composability requires that we have certain design features that enable something to be plugged into something else, okay? Another thing that defeats composability is concurrency. Anyone know what concurrency means? What does concurrency mean, especially in a software context?
Maybe making changes.
Making changes, multiple things at the same time. That's correct, Wyatt. Concurrency means we have many things running at the same time. Another word that we use that means a similar thing is parallelism. Right? Parallel software means that we're taking advantage of multiple cores, for example. So we all have multiple core computers in our pockets these days, right? Our smartphones have multiple cores. Writing programs that run in parallel on these cores is really important if we want them to be fast, right? Or faster than they were. Writing concurrent programs, it turns out, is really important to be able to do correctly if we want to write faster programs, but it can also be really hard to do. These days, most of the programs that we write have both state and have concurrency. Unfortunately, if we don't manage these two things properly, and I'm glossing over a lot of little details, but suffice it to say that if we don't manage state and concurrency properly, we can add a lot of accidental complexity to a project. Accidental complexity is complexity that is on top of whatever the sort of necessary complexity exists, right? Writing software is already pretty hard. The last thing you want to do is make it even harder than necessary by sort of dealing with these problems in, well, the wrong way, right? Now, related to this, I like to ask students this question. So imagine that you're a project manager. So you've graduated, you've taken on a job, right? You've worked your way through, you know, sort of junior level programmer, and now you're a project manager. So you're managing a bunch of programmers, okay? And let's say, you know, your company has decided that they're going to release a new piece of software in a month. And unfortunately, your team is far behind schedule. You're responsible for 5 programmers, and you're working them to the bone, right? They're coming in, they're working 10-hour days, 12-hour days. They're churning out code as fast as they can. But you're still behind schedule. So what do? You have plenty of money. What do you do? Thoughts?
Hire more people.
Hire more people. Yeah, that's sort of the obvious thing to do, right? You got plenty of money. Let's just hire more, either by outsourcing or hiring more people in-house. What do people think? Is that a good idea? Any arguments against that sort of fairly intuitive move? Diminishing marginal returns. Good. That's a fancy way of putting it. You're not wrong. Can you explain, or anyone else want to jump in? What happens when you start hiring more people? Okay, Matt, incentivizing current employees with bonuses. I mean, unfortunately, they're already working 12, 15-hour days. Like, it's hard to incentivize them even more, right? Very good, Jacob. It works to a point, but eventually, you're right, they get in each other's way. Indeed, if we have 5 programmers, imagine we hire 5 more. First of all, we have to train the new 5 programmers. They have to find a way to work with the existing 5 programmers. And then we have this big network of communication that needs to be worked out. It's actually really hard to add more programmers to a job and keep things as efficient. There's a very famous book that addresses the so-called mythical man month, right? Where a man month is, well, the amount of time a person works in a month, right? So presumably, if you can just hire more people, and therefore, you know, instead of 1 man month, by having 1 developer working on a project in a month, you can have 10 people generating 10 man months worth of code within 1 month. Okay, a very famous line from this book by Frederick Brooks is that our estimating techniques fallaciously confuse effort with progress, hiding the assumption that men and months people and months, better way of putting it, are interchangeable. Adding manpower to a late software project makes it later. Frederick Brooks famously managed a very large operating systems project, and that project was late by years. And this continues to happen. I mean, we have a lot of interesting software project management approaches that try to minimize delays like this, that try to push software out as soon as it's available so that we have prototypes so they can be tested, all right? So we can iterate instead of try to build this large monolithic thing and release that. But the truth is, and you asked the right question, David, what do you do then? Like, if you can't just hire more people, what do you do? Well, you plan better, right? You try to build things in pieces, okay? You try to iterate. You try to come up with ways where you're not building this gigantic monolithic thing. We have plenty of modern software engineering approaches that attempt to minimize delays like this, but the truth is, when it comes down to it, we are not very good at predicting how much work goes into certainly the more complex types of software projects. If you're building a simple web application where all the pieces are well tested, right, that's probably not a big deal. If you're building something that's very algorithmically complicated that still requires research, the truth is that, and the point that I'm trying to make here is that we should, as much as possible, try to minimize the unnecessary complexity on projects. All right, let me just glance through the other comments here. You could find or buy something that is reusable, very good. Try to remove complexity, excellent. Presuming we're coding and not testing, I'd move on from testing, make sure what was completed on schedule was rock solid, reduce the deliverable, try to have the best release possible for what can be written and bug fixed on time. Very good. So sort of go back to the drawing board in a way, sort of work with the client, maybe figure out, hey, can we reduce what we need as a minimum viable product, right? So-called MVP, right? Excellent ideas, everyone, right? So how can we manage complexity? These are things that people have already mentioned. Testing. Testing is one huge way of managing complexity. We tell this to students all the time. Unfortunately, this is not something that we see all the time or as much as we'd like to in academia, but a rule of thumb in proper software engineering and good software engineering is write tests galore. Write them before you even start writing code, right? Before you start implementing your actual product. That way, you know, once you start building the thing that you're going to be testing, whether or not it's working correctly, right? Employ better tools. This is incredibly important. A lot of people say we'll take a low-level class and immediately start using those because it makes sense. You're excited, right, to use the first set of tools that you've learned about for programming, right, to start writing, implementing pieces of software. But unfortunately, a lot of the fundamental low-level stuff, well, is very verbose. It requires that you do a lot of work to accomplish very little. And so it's important to sort of learn, you still have to go through, you have to jump through all the hoops, but it's important to learn what tools are best for certain types of jobs. Okay, for example, if you want to do concurrent programming, it's best to use some sort of lockless programming paradigm. Okay, this is something that I talk about in operating systems, in fact, which is a high-level class. There are ways of doing concurrent programming that don't involve sort of classical low-level error-prone mechanisms. For instance, message passing and asynchronous programming are two forms of concurrent programming that are very popular today. There are high-level parallel programming specifications that we can use. And there are patterns that are derived from functional programming tools. For example, some of you may have heard of MapReduce. It's something that Google popularized that really was taken from the functional programming paradigm as a way of writing high-level tools that inherently have a lot of parallelism and yet avoid a lot of the accidental complexity that exists when you write code using the wrong tools. All right. At the end of this lecture, the assignment that I give, I don't have the example here, but students get to play around with concurrent software and see what sorts of really weird, insidious errors come up There are these errors known as race conditions that arise when you have code that's running in parallel, and they manipulate things. And so if one code gets there first before the other, you end up with one result. If the other gets there first before the second, you have another result. That type of bug is really insidious and hard to detect. And the best way of dealing with it is simply to avoid writing code where race conditions are even possible, right? But of course, to get there, first you have to understand the fundamentals, right? Which again goes back to the design of our CS curriculum. So that's a snapshot of the lecture and complexity. The last slide we have here, we have plenty of time for it, I think, is for more question answer. Are there any other questions you have about anything we've talked about?
So I could talk a little bit about the AI curriculum. You still start with the standard intro to programming sequence and a discrete math and data structures. But you don't do the system sequence, it's not a requirement. And then the AI courses you're going to be taking, you still have to take a database course, but then you take a data mining course, you take an AI, intro to AI course, a natural language processing course. And then there's also a requirement for it's like an AI breadth course. So there's like an AI topic, but not in a computer science field. So it's like linguistics or learning theory out of the psychology department, things like that. So that's kind of the sequence of the required courses. There's tons of electives here with machine learning and graduate natural language processing and deep learning and all these types of things. But it's basically you start with the same programming sequence. Oh, you also take, I think, Michael, your 340 is a requirement for AI, right? So you're going to take this functional programming course that's an elective for CS majors. Let me look at some of these other questions. So how common to do a major and a minor? The AI degree does require a minor, the CS degree doesn't, but the CS degree has 4 free electives, so it's fairly easy to minor in something if you want to. Difference between ITM and CS. ITM is information technology and management. It's different from computer science. ITM is, like it says, it's technology driven and management. They take some management courses also. So technology is different from computing. Technology is like the final implementation of the computing. So their courses are more hands-on technology driven, where ours are more, I mean, you can see the type of stuff we're talking about, a little more theory side. We certainly do practical things too, but once you take a course in each, you kind of see the difference between the two.
The question about comp sci facilities, about supercomputers. Supercomputers, you might want to add to this, but very quickly, supercomputers look very different now than they used to. These days, they're very often task specific. We have a teaching cluster that you can get accounts on. We have a variety of different servers that we use. Some classes just use a dedicated server. All of our research faculty generally have their own labs, and many of these labs also have clusters of sort of GPU heavy computers, CPU heavy computers. Some professors deal with system related stuff, so they have very low level clusters of computers or just individual computers that you would probably consider supercomputers if you sort of look back in history and thought about what does a supercomputer look like. But yeah, there are a number of different clusters, but a lot of them are specific to labs and the research professors that do their work on those labs. What language would best prepare us for the fall? I would imagine if you're taking CS 115, 116, or 201 in the fall, the answer would be Java.
So I could talk a little bit about the economic benefit. I mean, I'm seeing, at least from students reporting to me, that the students who get the co-terminal and get the master's degree, you're talking a good 10% more on your first salary. Okay, so I mean, there's that benefit there. There are companies who are specifically looking for master's degrees because they're looking for that depth that you get with doing the graduate program. You're going to be taking not just one algorithms class or one systems course, you're going to be taking multiple ones. So they're looking for that depth. Some students don't get the co-term and end up working side by side with someone who has a bachelor's degree, but maybe they might get a little more money because they already have a master's degree. So, I mean, the degree itself is not going to necessarily determine your first job in your career, but usually it's a little more money associated with getting that co-term, that master's degree. Difference between CIS and CS. Okay, so they're both Bachelor of Science. Okay, so the IIT mostly offers Bachelor of Science degrees. The differences in computer information systems, I would say it's not an engineering degree. Computer information systems doesn't have all the math requirements and doesn't require all the 400, the upper level theory CS courses. You could take them as electives, but they're not required. So the CIS degree, what you might see at some other schools, it's more of like a liberal arts computer science degree. You can still take a lot of CS courses. There's the same number of CS courses, but the theory courses at the 400 level aren't required. You pick and choose. And you don't have to take all the math. The CS degree is an engineering degree. You got to take 6 math classes, 6 college level math. The CIS degree, you take 2. So I mean, tons of companies come for internships for recruiting. I mean, both through the CS department, we list opportunities. Through our career services on campus, there's opportunities. I guess at least pre-pandemic, they have a couple career fairs on campus, one in fall, one in spring, and the computing opportunities grew so much they had a separate day just for computing related hires. Because it's even I mean, regular mechanical engineers and chemical engineers, they could get a computing job too if they take like minor in CS or something. So I mean, the companies are all over the place, from like Google and Microsoft and big name companies like that to finance and to entrepreneurial to consulting. It's all over the place.
Yeah, I would say that there's also a fair number of sort of local Chicago area fintech, biotech companies represented, so yeah, there are quite a few. I mean, there are even alum, right, that come back to IT and recruit students from IT.
So our undergraduate degree in AI, it's fairly new. It's like it's in its 2nd or 3rd year, and there's only a handful across the country who have a Bachelor of Science in AI. Only a handful of universities that do. And so we're still waiting to see what the career opportunities are for AI. Now, I mean, in general, you might think it's a little narrower than a CS degree. The CS degree is broad. The AI degree, you're kind of a little narrower, but there certainly are opportunities in AI. So, we're anxious to see too exactly, if you have an AI degree, is that going to exclude you from certain opportunities, but expose you to other opportunities? You get a CS major in a computational chemistry. Yeah. There's minors in computational chemistry and computational physics and applied math. I see Michael Pell's major joined us. He's from applied math department, so he always wants us to push. I mean, CS and applied math is a great combination. Okay, so the accelerated, if you have any kind of programming background, even in a drag and drop language, if you know if statements and loops, you probably have enough background to take the accelerated. You'll send me some coding samples and I help determine if you should take the 2-semester sequence or the 1 semester. Michael, you want to talk about student orgs and things?
Sure. So I'm the advisor for the ACM organization at IIT, which mostly consists of computer science majors. ACM, Association for Computing Machinery, is an international organization supporting research in computer science. There are plenty of student-led organizations related to CS, ranging from just sort of your Linux working group to robotics groups, those focused on running hackathons, attending hackathons, sort of working on specific frameworks even, like we have, a React student organization, a Flutter student organization. Our Discord server, which I think some of you have already seen, has quite presence from a lot of these student organizations. They have regular announcements. Obviously, over the past couple of semesters, they've been doing all their general body meetings online. But absolutely, there are a fair number of student organizations related to CS. As far as learning opportunities too, as I said already, a lot of these student organizations focus on learning opportunities. So they run, sort of mini seminars, tutorials and demo sessions on how to use various platforms and tools, say for building apps or, that type of thing. But it's also, since we're a fairly small department, it's also one of those things where you could probably approach a professor as well, to talk about opportunities for extracurricular learning.
You can always email Michael or me, if you have further questions. We can even set up a time to chat. So thanks everyone for joining us tonight.